Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So this is a portion of distributed forces. So still on locating centroids of volumes, areas, arcs or lines, and the corresponding derivation of formulas for volumes as well as for the locations of the centroids or center of gravity, which is very important in the succeeding topic on uh, beams subjected to loadings, line loads, concentrated loads, or surface loads. Level 36 problem. Determine the x-coordinate of the centroid of the solid spherical segment. Evaluate your expression for h equals r over 4 and h equals 0. So here is the figure, and let's draw the view in the z direction, from the z direction, so that we can analyze the situation. So this is a solid spherical segment. We call this spherical segment of single base. So this is that portion, and the distance from the y-axis or the central axis is, from this y-axis here is h, the radius is r. Then we have a strip horizontal, then have it revolve about the x-axis so that it generates this disc, circular disc. So the thickness, it cuts the x-axis, so dx, the height is just y, or the radius is y. Then we use spherical coordinates here, or polar coordinates. So that's dx, and that radius is r. This distance is from center to centroid of this, or any point on the plane of this circular disc, is x, so that we can relate x, y, and r by Pythagoras theorem. So volume equals volume of this, which is pi y square, pi radius square times thickness dx. And from the figure, y square is r square minus x square by Pythagoras theorem. So integral from h to r of pi, then y square is r square minus x square, then times the thickness dx. So therefore, for volume is pi, quantity r square x minus x cube over 3 from h to r. Substituting limits, so pi equals pi, quantity r cube, r squared times r is r cube minus r cube over 3, minus lower limit minus quantity r square h minus h cube over 3. So this is 2/3 r cube, so volume equals 2/3 r cube minus r square h plus h cube over 3. Simplifying further by factoring out 1/3, so we have volume equals pi over 3 quantity 2r cube minus 3r square h plus h cube. So that's the volume in general. Then by Pythagoras theorem, volume times x sub c, x sub g rather, equals integral of x sub c differential volume. So x, because the centroid anywhere of this differential element, which is the disc, is equidistant from the y-axis, so that distance x, this is also x, that's also x, from the bottom x, x, so therefore x is just x sub c. So volume xg equals integral of x sub c dv, where x sub c is just x, so pi over 3 quantity 2r cube minus 3r square h plus h cube times xg equals the integral of x from h to r of dv, which is pi quantity r square minus x square. Distribute, cancel out pi, So 1/3 quantity 2r cubed minus 3r square h plus h cubed xg equals integral of r square x is r square x square over 2. Integral of x cubed, so minus x cubed dx integral is negative x to the fourth over 4 from h to r. So 1/3 of quantity 2r cubed minus 3r square h plus h cubed times the quantity xg equals r to the fourth over 2 minus r to the fourth over 4 minus r square h square over 2 then plus h to the fourth over 4 because this is minus quantity. So that's the result, combining r 1/2 r fourth minus 1/4 r fourth, then that's 1/4 r to the fourth, so 1/3 quantity 2r cubed minus 3r square h plus h cubed xg equals r to the fourth over 4 minus r square h square over 2 plus h to the fourth over 4. Simplifying the right part by factoring out 1/4. So you just copy this. Then xg equals 1/4 quantity r to the fourth minus 2r square h square plus h to the fourth. So take note that this is a perfect square trinomial. The factor would be quantity r square minus h square raised to 2. So therefore xg is 3 times quantity r square minus h square quantity square, which is this perfect square trinomial, divided by 4 of this. So that's the value of xg. Then let's check the expression for h equals r over 4. So h is r over 4. Then xd is 3 quantity r square minus r over 4 quantity square, then quantity square, close quantity square, divided by 4 quantity 2r cubed minus 3r squared times r over 4 plus r over 4 cubed. So simplifying this using the calculator, then xg is 25 over 48 of r. Then when h is 0, it becomes a hemisphere. And remember that for a hemisphere, the location of the centroid is 3/8 from the base of the hemisphere to the centroid of the solid hemisphere. So let's check. When h is 0, this is xg would be 3 quantity r square quantity square over 4 quantity 2r cubed, then the rest is 0. So this is 3r to the fourth over 4 over 8 r cubed. So 3r to the fourth over 8 r cubed is 3/8 of r, which checks for the location of the centroid of a hemisphere. So that's it for this problem. Level 37, determine the x-coordinate of the mass center of the portion of the spherical shell of uniform but small thickness. So this is the spherical shell, uniform and small thickness. So the thickness is 3/4 of, the height rather is 3/4 of r. Then because the shell has small and uniform thickness, instead of volume of the material, we can compute the surface area instead, locating the surface centroid of the surface area. That's also the location of the centroid of the material because the thickness is small and the volume of the material is simply surface area times that thickness. So we can use surface area instead of the volume of the material in computing the volume, in computing the surface area. because anyway, the volume of the material is simply surface area times thickness. So let's draw the view from the z axis. So this is it. This is the portion of the spherical shell, and this is r over 4. So this is the strip ds, then rotated about the x-axis to generate this surface. The length of the element here is ds, then the distance from the x-axis, the radius in other words, or the distance of that differential s from the x-axis is y, and that's also the radius of revolution. Then we use polar coordinates here, so that's the radius. The central angle is differential alpha, so this angle is alpha, so that's ds. Because this is an element of an arc of a differential sector, so it is just the product of radius and the central angle. So ds is r times differential alpha. If this is alpha in general, then y is radius hypotenuse times sine of alpha from the figure. So this distance is x, and x is r cosine of alpha from the figure. And that's also the location of the centroid of the differential element. So x is just x sub c, and x is r cosine alpha. Remember that. So x is just x sub c. So S sub a is integral of differential surface area. The surface area is equal to the length of the element ds to be revolved about the x-axis, and the distance traveled by the centroid, or the circumference of this circular path, is 2 pi times y, or 2 pi times r sine alpha. So surface area equals integral from r over 4 to r of 2 pi, because we have one revolution, times y. This is the length of the path, times the differential length of the element ds. So from Pappus-Goldini's proposition, although it's not yet introduced, but this is supposedly the surface area, length times length or thickness of path times the total length of the curve, which is 2 pi, or circumference 2 pi times y. So remember this expression from integral calculus. It is just reviewed here, and I hope that you can recall the expression for surface area. So it is the length of the differential element times distance traveled by the centroid, in this case circumference of this circle, which is 2 pi times radius of revolution, 2 pi times radius of revolution, which is y. So ds is square root of, I'll use 1 plus dx dy quantity square. Let's make x the variable rather. So integral from 0 to theta of 2 pi, y is r sine alpha, then ds, which is r differential alpha. So let's make the angle alpha as the variable so that we can easily evaluate the integral. So this is 2 pi r square, so that's theta. So S surface area is integral from 0 to theta of 2 pi r sine alpha times r differential alpha. So 2 pi r square, integral of sine alpha differential alpha is negative cosine alpha from 0 to theta. So 2 pi r squared negative of cosine theta minus cosine of 0. Cosine of 0 is 1, remember? And cosine theta from the figure is r over 4 over hypotenuse r. So cosine theta is 1/4. Substitute here. Surface area is 2 pi r squared of negative quantity 1/4 minus 1. Cosine of 0 is 1, remember. So this is 3/4 times 2 pi r squared. So that would be 3/2 pi r squared. That's the surface area. The direct formula for surface area is from zone area 2 pi r h, where h is the thickness, which is in this case 3/4 the thickness. So 2 pi r times 3/4 of r, 2 pi r times 3/4 of r is 3/2 pi r squared. So which checks from the direct formula. Then by Varignon's theorem, surface area 3 pi r squared x sub g equals integral of x sub c differential surface area. From the figure, x sub c is just x. X sub c is just x. So 3/2 pi r squared xg equals integral of x times 2 pi y ds. Substituting, remember that x is r cosine alpha. So 3/2 cancelling out pi, and let's have 2 times 2 here. So this is now 4. So 3r squared xg equals 4 integral of x, which is r cosine alpha. Then y is r sine alpha. Then ds is r differential alpha. So xg equals negative, because the integral of negative cosine alpha sine alpha differential alpha is like cosine alpha times negative sine alpha differential alpha. Remember that the differential of cosine is negative sine alpha differential alpha. Let's make it that way. And actually it's positive because we factored out negative 1. So that this is now in the form u differential u, and the integral is u squared over 2. Cosine square alpha over 2 from 0 to theta. So this is the simplified form, because this is 4r cubed divided by 3r squared, so 4r over 3. Then let's just proceed the negative sign because the other negative sign is here. So xg is negative 4r over 3, then quantity cosine square of alpha over 2 from 0 to theta. Remember that when theta is theta, cosine theta is 1/4 from here, and cosine of 0 is 1. So xg is negative 2r over 3, quantity 1/4 minus 1. So minus 1 square. So simplifying, xg therefore is equal to negative 2/3 r times negative 15 over 16. So xg is equal to 5/8 of r. So that's the answer to this question. Let me generalize the situation. If you encounter the same, then you can easily locate the centroid of the surface area of a portion of this sphere. So if this is the spherical segment with 2 bases, remember that we call this surface area as zone area in general. So the centroid is here. If the thickness is h from the figure, then the distance from the centroid to the left base is equal to the distance from the centroid to the right base in general. So that's a fact. And because the zone area is 2 pi rh, it depends on the thickness. So the thickness must be the same so that the area of the portion lying to the left is equal to the area of the portion lying to the right. So this is h over 2, h over 2. So that's why here in the original problem, the thickness of this zone or surface area of the spherical shell is here, and because the thickness is 3/4, half of 3/4 is 3/8. So 3/8, this is 3/8, half of 3/4, because this is 3/4 the thickness. So half of 3/4 is 3/8. 3/8 plus 1/4 is 5/8. So that's why we have xt is 5/8 of r, and that is r over 4 plus half of this thickness, half of 3/4, which is 3/8 of r. So 1/4 of r plus 3/8 of r is 5/8 of r. So I hope that you can now generalize it as your experience. So for this situation, if this is known, this distance is known, then the distance between these parallel bases is also known. So the location of the centroid is simply this distance plus half the thickness of this zone or zone area. Level 38. The thickness of the triangular plate varies linearly with y from a value TO along its base y equals 0 to 2TO at y equals h. So determine the y coordinate of the center of the mass of the plate. So this is the plate, and if you look at it from this view, end view here, the thickness varies. So for the solution, let's divide this into two parts, so that we have a plate, triangular plate of uniform thickness, and another triangular plate of varying thickness from 0 at the base, y is 0, to the thickness here would be T sub O, 2TO minus TO, because we divide the plate into two parts, one of uniform thickness TO and the other of varying thickness from 0 to TO. So let's call this V1 and that part V2. V1 is area of the triangular plate times constant thickness TO. So 1/2 base times height, that's the top view area, times the thickness TO, so it becomes volume. So 1/2 BH times TO. So V1 is BH TO over 2. So of course, the location of the centroid is the location of the triangular area because the thickness is uniform. So XC1 is 2/3 OB, then YC1 is H over 3, although we are only asked for the Y coordinate of the centroid. You might be asked for the X coordinate of the centroid. So XC1 is 2/3 OB, then for that element, and Y sub C1 is 1/3 of H, which is the same centroid as that of the triangle because the thickness is uniform. While for V2, it's different. So let's have a strip. So it is area times the thickness, which is varying also. So this is the strip, horizontal strip. Then let's project it. The thickness is dy. The distance from the y-axis to this end is left x supposedly, so we'll just call it x because the left x is 0. And the right x is b. That's b. Anywhere on this vertical line, the distance from the y-axis is b. Therefore, this is b minus x, the length of the strip. And the distance of the centroid of this strip from the x-axis is y. From the left, y. From the center, y. From the right, it's also y. So that's why it's constant at y. Then that's dy. Then this is b minus x. Then we have here the strip of thickness dy, and this length is, let's just call that z, because that's the z direction. So z, I hope that you can clearly see it. Then let's because it is y that is the variable of integration, let's express everything in terms of y. X in terms of y and z in terms of y. So from the figure, so that's TO, 2TO minus TO. So for this triangle here, the base at the top is TO. So differential volume 2 equals integral, or differential volume 2 is area of this strip b minus x times dy times thickness perpendicular to the board, which perpendicular to the screen, which is z. So b minus x times dy, that's the area of the strip, times thickness perpendicular to the screen, z, which is also a variable. So x must be expressed in terms of y, z must also be expressed in terms of y. So from the figure, x as to y equals b as to h. So x as to y equals b as to h. So x is b over h times y. Likewise, from this triangle here, z as to y equals to as to h. The height is h. So z as to y equals t sub o as to h. So z is to over h times y. So that differential volume 2 is quantity b minus b over hy. Then z is t over hy dy. Factor out b, to over h, then distribute y. So dv2 equals b to over h quantity y minus y square over h dy. Integrating, v2 equals b to over h quantity, so integral from 0 to h of y minus y square over h dy. So v2 is b to over h quantity y square over 2 minus y cube over 3h from 0 to h. Substituting, v2 equals bto over h quantity h square over 2 minus h cube over 3h. So these are like terms, minus lower limit, everything will be 0. So 1/2 minus 1/3, 1/6 of h square times bto over h. So v2 is bto h over 6. So the volume total would be bh. Let's locate the y coordinate of the other volume. So by Varignon's theorem, bht over 6 y sub c2, because we do not know the location of the y coordinate of the centroid of this second part, with varying thickness. So y sub c dv2. Then y sub c is just y, because from the left it's y, from the center it's y, from the right it's y, it's constant. So that's the location of the centroid of this differential element. So y is just y sub c. So vhto over 6 y sub c2 equals integral of y. Then dv2 is equal to this, not yet evaluated. So bto over h quantity y minus y square over h. Then distribute y, integrate. So cancel out bto. What is left is h over 6 here. Y sub c2 equals 1 over h. Then integral of y square minus y cube over h dy. So y sub c2 equals 6 over h square, then quantity y cube over 3 minus y to the 4th over 4h from 0 to h. So that would be 112 h cubed times 6 over h squared, so that would be h over 2. So simplifying, y sub c2 is h over 2. And we now apply Varignon's theorem because we have located the centroidal distance y coordinate of the centroid of the other plate with varying thickness from 0 to TO, 0 from the base to TO at the top. So the total volume is BHTO over 2 plus BHTO over 6. So it is 2/3 BHTO. So 2/3 BHTO times YG equals BHTO over 2 times H over 3 for volume 1. Y sub C1 is H over 3 plus volume 2, which is BHTO over 6, and its Y coordinate is H over 2. So cancelling out BHTO, so 2/3 YG equals H over 6 plus H over 12. So finally we can now solve YG. YG is equal to 3/8 of H. So that's the location of the Y coordinate of the centroid of this plate. Level 39, locate the mass center of the homogeneous solid body whose volume is determined by revolving the shaded area through 360 degrees about the z-axis. So this is the shaded area to be revolved about the z-axis. This is the z-axis. So let's have a vertical strip so that when this strip is revolved about the z-axis, by the way, the radius or the height is r, and therefore the thickness is dz. It generates a circular disc of radius r, thickness dz, so the differential volume is pi r square dz. So that's dz, and this is the generated shape element, which is a circular disc. So this distance is simply z, and let's locate g. Let's derive g sub z. Xg by symmetry is 0 and Rz is also 0. So let's just have let's just have g sub z. So volume equals integral of pi r square dz. So integral from 0 to 300, the variable of integration is z. So 0 to 300 of pi r square dz. Then the value of r is given by this expression. So let's evaluate k first. At this point here, r is 200 and z is 300. So 200 equals k times 300 cubed. So k therefore is equal to 1 over 135,000 mm to the negative 2. So substitute here. Volume equals pi integral from 0 to 300 of z cubed over 135. This is k 1 over 135,000 mm to the negative 2. Then because this is r square, so quantity square. So using the calculator directly instead of manually evaluating it, although it's easy to evaluate because this is g to the 6 over 135,000 square. So the integral can be easily evaluated, but let's use immediately the calculator. This is the result. 1.2 times 10 to the 7 pi over 7 mm cubed. Then by Varigdon's theorem, volume 1.2 times 10 to the 7 pi over 7 z sub g is integral of g sub c dv, where g sub c is just z on the figure. So 1.2 times 10 to the 7 pi over 7 z sub g is integral of from 0 to 300 of z pi z cube over 135,000 quantity square dz. So again, using the calculator, cancel out pi first, then we can evaluate g sub z equals 262.5 mm. So I will leave the details to you because this is just power formula and it's a matter of substituting these values using your calculator. Level 40, the homogeneous slender rod has a uniform cross-section and is bent into the shape shown. So calculate the y coordinate of the mass center of the rod. So here is the figure. So we'll find the length because the rod is homogeneous. So the location of the centroid of the length is also the y coordinate, is also the coordinates of the centroid of the mass center of the rod, because the rod is homogeneous, meaning uniform cross-section and constant density. So S is integral of ds, and the formula for ds is square root of either square root of 1 plus dy dx square dx, or square root of 1 plus dx dy quantity square dy. So I'll use dx dy here. So that's ds, and s is integral from 0 to 100 of 1 plus x prime square, or dx dy square times dy. The original formula is, if you enlarge and magnify this, that's the hypotenuse ds, the horizontal projection is dx, the vertical projection is dy. So ds is square root of dx square plus dy square. If you multiply everything by dx over dx and the denominator dx put into the radical, then it becomes 1 plus dy dx, square root of 1 plus dy dx square dx. But if you multiply dy over dy and put the denominator dy into the radical, then it becomes 1 plus dx dy quantity square times dy. And again, that's your part because that's from integral calculus, and you are already expert on that supposedly, because you are now in statics. So let's evaluate k. At this point, x is 100 and y is 100. So 100 equals k times 100 square. So k is 1 over 100. So that means x is y square over 100, or 1 over 100 y square, so that the derivative dx dy is y over 50. 2y over 100, or y over 50. Substitute. S is integral from 0 to 100 square root of quantity y over 50 square dy. So using the calculator, because that's allowed, instead of manually evaluating it, so S is 147.89 mm. Then by Varigdon's theorem, SYG equals integral of y sub c ds. SYG equals integral of y sub c ds. Because ds is like a point, so x sub c is just x, y sub c is just y. Because as I said, this differential element s is like a point. So y sub c is just y, x sub c is just also x if x coordinate of the centroid is to be located. So 147.89 yg equals integral from 0 to 100 of y square root of y over 50 quantity square dy. So this can be evaluated by power formula. If you let u be 1 plus y square over 50 square, then the differential is something about y dy. You can evaluate that by power formula if done manually, but you are through with that in integral calculus. That's why the calculator is allowed. You can use the calculator in evaluating this integral. So 147.89 yg, the value of the integral at the right using the calculator is 8486.617. Therefore yg is 57.36 mm. So that's it, because the video is a bit longer.